Hi everyone. Today we're going to be going over the acceleration of a yo-yo and how to find it. So I got my little yo-yo drawing. Looks pretty fabulous if I say so myself. And then I have a side view of the same yo-yo, that string going up off that center cylinder. And I have that center cylinder, just that dotted circle around like that. And so first we got to think about how a yo-yo works. So the yo-yo has the string wrapped around that center cylinder, and then as the yo-yo rolls down, it starts to gain angular speed, gain linear speed also. But we can think about that string isn't slipping around that cylinder. So since it's not slipping, we can say the yo-yo is rolling without slipping. So that is a key idea that we'll need to think about as we go through this problem. So the first thing we want to look at to be able to find the acceleration is what are all those forces acting on this yo-yo. So we already know that, we already know what's pulling it down, that force of gravity, right? So we have a vector pulling it downward with some magnitude, mass times gravity. Or let me write it out over here. So mass times gravity. And then what would be pulling it up? So we have that it's attached to a string that's going up, which would be attached to your finger. So we can say that there's some force pulling it up, and we call that force tension. And we can see that those should be the only two forces acting on this yo-yo, neglecting air friction and friction along the string. And we're also assuming that the string has a negligible mass. So this will be an ideal yo-yo. So now that we have our force diagram, we can look at Newton's second law, or that sum of the forces. We know that F equals mass times acceleration. And this is the total mass and total acceleration of the system. So total acceleration of that yo-yo falling down. Then I want to add up all my forces. So I'll take the mass times acceleration as positive, so it's accelerating downward. So my mg will be positive since it's in that same direction. And then tension is in the opposing direction. So I'll say mg minus t. So we already have one equation set up. We notice we have acceleration and tension, which we don't know either of. So we need to get another form or another equation with tension in it. So we can see that the tension is off center from that center axis of the yo-yo. So we can say that tension causes torque. And remember, using torque concepts, we need a moment arm. So that moment arm, we need to be perpendicular to that tension and going to the center of the yo-yo. So it should be right there. That small moment arm going from the center to that outer portion of that small cylinder. So we'll call that little r. Little r. And using torque concepts, we can say the sum of the torques should be equal to moment of inertia times alpha. So this is the rotational form of Newton's second law. You can say the sum of the forces equals mass times acceleration. Over here, the sum of the torques equals moment of inertia times angular acceleration. And then we just want to add up all our torques. So we can see that tension is the only torque acting on this yo-yo. So we get tension times its moment arm, so little r. Now we have an expression with tension and acceleration in it. So solving for tension, so I can plug it into my force equation over here. We want to divide by r both sides to get T equals I alpha divided by r. So now I can plug this in to my force equation. So we should get mass times acceleration equals mass times gravity, then minus my equation for tension. So that I alpha divided by r. Now, we have two different kinds of acceleration in here. But since it's rolling without slipping, we can relate those two accelerations. So if you recall, we can use the relation A equals r times alpha, where r is that little radius. So substituting this in to our equation up here, we can get mass times r times alpha equals mg minus I alpha over r. So we see now that we only have angular acceleration in our equation. Now I'm going to solve for it. So I need to get all my like terms on one side, or all my accelerations on one side. So I'll add I alpha over r. So we get m r alpha plus I alpha over r will equal mass times gravity. Now, to isolate that angular acceleration, I want to factor it out. So factoring, we get alpha times mr plus I over r. And it still equals that mg. Then, solving for alpha, I want to divide by mr plus I over r. So we can end up with alpha equals mg over mr plus I over r. And here is our equation for angular acceleration. So we can have, or we can find what that total mass of the system is. We could find or measure what that small radius is. That small radius. And we can calculate what that total moment of inertia is. So the total moment of inertia of this whole yo-yo. So using the concepts of moment of inertia of each of the individual discs and the moment of inertia of that center cylinder. So there is our expression for angular acceleration.